turn this on, so I'm going to need little reminders to make sure this light is blinking and everything's turned on. Okay, so please put Project 3 in the red folders or orange red folders, however you see color. Monday's quiz is on 17 through 21, but remember that Class 19 was not new material. Class 19 was just the in-class summary with some more problems of classes 17 and 18. So remember that class 20 came on the Friday after class 16. We changed the order there so that the long weekend didn't interfere with the transformation material. So today we're going to finish up inverse functions, class 22. Monday we're going to have our quiz, and then we're going to have a fairly short lecture on two formulas that are useful, the distance formula and midpoint formula. And we're going to look at how to find equations for circles. So Monday's lecture will not be as long as usual. For midterm grade information, please set up an appointment to come see me. I will show you all of your averages. We can set up a plan and a schedule for a new check-in time. Remember, November 8th is the last day to withdraw from any of your classes with a W. So we will have another exam. So by next week, we should have a fairly good idea. We'll be 2/3 of the way through of where you are. Now remember, that first exam is counting 40%. So if you didn't do well on the first exam, after Friday, November 1st, next Friday, that's only going to be 20% because your new tests will come in. So if you want to see me anytime, even if you think you have an A+ for an average, that's fine. Anyone's welcome to come see me, and I'll give you that information. Remember, the answer key for class 19 is sitting right up here on my desk, but you have to show that you've made some progress, C through G. And if you're not going to do that today or Monday or Tuesday or whatever, please make sure you work on this prior to next Friday's exam so that you can check out your knowledge of transformations. Okay. All right, so let's take a look at today's material. We'll start off by just reviewing Wednesday, sort of the two big ideas that we came up with on Wednesday. So our idea so far about inverse functions is we're either looking at a finite set of ordered pairs and we're switching the order of the variables, the input and output or dependent, independent variables, domain and range, to create an inverse. So visually what that looks like is if you have something in your first function in the domain, a value, your first function takes it out through some kind of magic to another output. And what happens with the inverse function, that's the blue line, is it brings you right back to where you started. So that was sort of the round trip idea of inverse functions. You end up right back where you started. So one of the ways of saying this is that the range of my first function, f, is the domain, because that's what goes into your inverse function, is the domain of your inverse function. Or the range of your inverse function, where you end up, is where you began, the domain of f. Okay, so another way of seeing this picture is to say, if you take the input A and you apply f to it, it brings you to B. And then if you apply the inverse to B, it takes you right back to A. So there's your sort of circular sort of reasoning, the round trip idea. So we spent some time working on that. We also mentioned that sometimes when you try to find the inverse, you don't always get a function. So you always got to be careful to check that when you try to swap your inputs and outputs, that you check to see that you have a function and not a relation. Then finally, we came up with this idea that we imitated the Ed Sullivan show. I am missing a set of parentheses. I noticed it after I printed yours, and I didn't want, did I fix yours? No. And I didn't want to waste any paper. I just figured you could put this parenthesis in right here. Is it? Okay, so I fixed it and just copied the first page again. Okay. One still missing? Okay. Okay, and then we realized that, hey, composition of functions in general, if you compose two functions, in general, the composition of functions, the order matters. They're not commutative. We discovered this when we did compositions of functions. But the big exception is inverse functions. If you have two inverse functions, you can verify, and this is how we actually define inverse functions, you can verify that indeed the two functions you're looking at are inverses of each other. Is when you compose them and you change the order of the composition, you come right back to where you started for both of them. That was the big idea. And this is how, anytime, if I ever ask you to verify that two functions are indeed inverses, you would just do these two compositions. And if they both give you x back, then you know they're golden, they're inverses. Okay, so that's the kind of stuff we did on Wednesday. Today we're going to take a look, again, a further look at functions, but start to look at visually, if we had a graph of a function, how would we know that it had an inverse? And then algebraically, how would we actually find the inverse of a function? So those are going to be the things that we look at today. Okay. So let's take a look at step 2 here. Okay. Many actions in life are reversible, right? Many aren't. I mean, if we have an explosion, we can't undo an explosion, right? Okay, we cannot. Huh? Right. If you have a time machine, right. Back to the future kind of thing. So this is just an example I've been using for years, and I usually kind of start with a bare foot and all that, but I'm not going to do that today because I don't know, I get strange looks. But suppose I told you that the action was to start with, here's a bare foot, and you can tell why I didn't go into art. There's my bare foot. That's where I start, right? What do you think about that? Yeah, I got a button for sure. Start with my bare foot, and then I put on socks. And then I put on my shoes, and voila, I have a foot that's got all set to go out and walk around. All right, I want to undo this. Where do I want to get back to? My bare feet, right. I want to get back to, so I want my final outcome to be my bare foot. I guess I don't even have 5 toes. I should get a little clip art of a foot. Okay. So this is where I want to end up. I want to do a round trip and end back up with a bare foot. So how do I undo this action? Right, I take off my shoes. So let's now take a look at this. The first thing I undo is the last thing I did. Okay, so the first thing I undo is my last action. Whatever my last action was is the first thing I undo. So I put on my shoes, so the first thing I have to do is take off my shoes, and then the first thing I did was to put on socks, and now I do the inverse of that, which is to take off my socks. And now I'm back to my original state. So I've performed my round trip. Okay, my round trip happened. Okay, back to my bare foot. So notice, to undo something, you do your inverse operation in the reverse order. So think about that for a minute. This happens every single time you solve an equation, a linear equation. If I say that I take t, if I start off with, well, let's start off with our famous dude x. So here I'm starting off with x. If the first thing I do to x is to double x, and then add 5 to it, so it looks like this, 2x plus 5, and I ask you to undo that, the first thing you would do would be to subtract 5 and then divide by 2. So you have been performing undo what's happened to x. In fact, I used to show this a lot in Math 105 or 095, that this process is what you're doing every time you solve a linear equation. So you think about evaluating your expression. If I gave you a number for x and you found the value of an expression, you would do it in this order. If you wanted to get back to where you started, you undo it. So when we're undoing mathematical operations or reversing the calculation, we use the same idea that we did with putting on your socks and shoes and then getting back to your bare foot. So let's do the following. Let's find the inverse of the following operation. So I'm going to subtract 9 from x. And then I'm going to multiply the result. Notice this word result, because that is going to represent something. I'm going to multiply the result by 5. Okay, so how do I undo this action? Well, we know we got to take our last action, which is multiplying by 5, and we've got to undo multiplication. And what's the inverse operation of multiplication? Division. So the first thing we're going to do is to divide by 5, and then we're going to undo subtracting 9, which is to add 9. So if I had a function that looked like this, here's my action. I'm going to start with x. I'm going to subtract 9 from it, because that's what it tells me to do. And I'm going to multiply the result. So how do I multiply the result? What do I have to do to this so I multiply the result by 5? Put it in parentheses, right? So this is what my first function is telling me to do. To start off with some number, take away 9, you get an answer, and then multiply the whole thing by 5. So until we have a value for x, we have to put it in parentheses. Okay, to undo this, its inverse function is going to start with x, and the first thing I'm going to do is divide by 5 and then subtract 9 from it. So that's what the inverse of f would look like. Well, how would I verify that these two things are inverse functions? How do I verify that? How do I prove to myself or to you that those truly are inverse functions? Set them equal to each other. Well, they'll never be equal. Yes, thank you. Plus 9. Add 9 to both, right? I didn't even follow my instructions, did I? Square them. What is this called? What are we doing to these functions? What does this notation represent? F to the negative 1 is inverse, but when I put two functions together in a sequence like this, they're composed, right? So when you compose your functions, that's what this little circle means. When you compose your function with its inverse, you should come back to x, and when you compose it in the opposite order, you come back to x. So what we want to do here is we want to compose these two functions. You have to prove that f of f inverse of x brings you back to x, and you have to reverse the order of that composition. You have to show that if you put f of x, use f of x as your inside function, and then you perform your inverse, that takes you back to x. And if both of these things are true, then you know you have an inverse. So let's do that. So let's start with this first composition. My inside function, the thing that's going into f, is called its inverse. So you go back up here and you say, okay, my f function says, this is how f operates. F says, whatever you give me, I'm going to subtract 9 from it, and then I'm going to multiply the whole thing by 5. So now what are you giving to f? This is what you're giving f. That's your input. So you go back to your f function, you see wherever x is, you put in f inverse of x. You subtract 9 from that, and you multiply the whole thing by 5. Okay. Now you say, well, what the heck is f inverse of x? And you look at your formula, and it says f inverse of x is this expression, x divided by 5 plus 9. So I'm going to replace f inverse of x with what it represents, x divided by 5 plus 9. Then I'm going to subtract 9 from it because that's part of f. And then I simplify all that junk inside the parentheses. So 9, take away 9 is 0. So this gives me 5 times x divided by 5. And we know that 5 divided by 5 gives me the number 1. So that brings me back to x. So now you're half hopeful. Okay, now you're half hopeful that these truly are indeed inverse functions. But you got to compose it the other way. So you've done that composition, and now you have to start with f of x as being your inside function and put that into your inverse function. So your inverse function says, no matter what you give me, I'm going to divide it by 5 and add 9. So let's take f of x and put it into our inverse function. So it's going to be f of x divided by 5 plus 9. So now I'm following the instructions, the recipe for my inverse function. And now to simplify this, I replace f of x with what it's equal to. F of x is equal to 5 times x minus 9. And now I perform the remaining pieces of my inverse function. So right away I see I have a foo-foo right here. 5 over 5 is 1. So what do I end up with here? I end up with x take away 9 plus 9. And that brings me to x. So I'm a happy camper. I've composed both of these functions. I've reversed the order of the composition, and they've brought me back to x. Okay? So that's how you verify that two functions are indeed inverses of each other. Now, you could start with a number like 2. And you could put 2 into this function, get your result, put that in here, and then you can reverse it. But all you're doing is showing that it inverses it for a particular number. Whenever you have to sort of prove or verify something in mathematics, you have to do it for all x's in the domain. So by doing it in this way, using your general expressions, you've shown it's true for all x in the domain, not a specific value. So any questions on finding that inverse? So these are the steps we're going to look at more formally later. This is just how you do it by looking at each individual action and reversing the order and undoing each one. Any questions at all before I move on? Okay. All right, so the next question that arises is whether or not every function has an inverse function. And from our last class, we saw the female literacy rate when it was associated with the nation, and then we reversed the order. We found out that it truly was not a function because we had 2 countries with the same female literacy rate. So when we reversed it, when we were at 99, it could have been Brazil or Germany, or I don't remember the countries off the top of my head. So we need to find some way to answer the question of whether 2 functions have inverses when we're dealing with mathematical functions and not just finite sets of pairs from a table. So here's 2 mathematical functions. Their solution sets are infinite because one is a line, x plus 1 is a line, so it has an infinite solution set because there's a zillion points on that line. That's really mathematical to say zillion. A zillion points on this line that satisfies the equation f of x equals x plus 1. And the parabola g has an infinite number of solutions, also represented by this graph. So if we do what we did the other day by just plucking off some individual ordered pairs from each function, you can see that if I have this function, here are 4 possible solutions. I could have picked any. So I said if x is -2 and I put it into my function, -2 plus 1 gives me -1. So that point, -2, -1 is a point on that curve, on that line, -2, -1. There it is. So here are 4 points that I've picked off of that line. -2, -1, -1, 0, that's the x-intercept, 0, 1 is your y-intercept, and then 1, 2 is just another point or another solution on that line. Okay. If I reverse the order of the coordinates, we swap the inputs and outputs, this is what we end up with. And if you recall, we had to look at each ordered pair and say, Is it a function? And you could, so we look here. Well, it looks pretty good to me because every different output, every different input here, -1, 0, 1, 2, has a different output. It's unique. So that means the inverse, this line, has an inverse that's a function. So that's cool. Okay, so that has an inverse that's a function. This is what we did the other day on Wednesday. So the line works. What about the parabola? So again, I've plucked off 4 solutions to this equation. I put -2 in here for x. -2 take away 1 is -3, and when I square it, I get 9. So I just plucked off 4 points from this parabola. Let's put those in red. -2, 9 is somewhere up here. And -1, 4 is right there. And 0, 1 happens to be the same point as where the line is. And 4, 3. 4, 3 is, oh, doesn't seem to work. 4, take away 1 is 3. Oh, it's 4, 9. Did I really do this? No, 4, 3. All right. For some reason, it's not showing right on this graph. Oh, thank you, 3, 4. I'm already thinking of the inverse function. I'm looking down here. Okay. So there are 4 solutions. And as we know, if we connected all of those red points with a smooth curve, we'd get this nice, beautiful parabola. And you also know what this parabola looks like because you've now done transformations. You wouldn't have to plot all these points. You know that it's been shifted to the right 1 unit from your parent function, x squared. And that's exactly what's happened with this parabola. Okay, so now if we look down here, after we swap the input and the outputs, you look to see if this defines a function. And the answer is that it does not define a function, but can someone tell me why these 4 ordered pairs do not represent a function? There's 2 4s, okay, well, it's not the fact that there's 2 4s, but what is it true about? So if you put a 4 into your inverse function, what's going to come out, Tiffany? Tiffany. You put 4 in, what comes out? What comes out when you put 4 into this inverse function? -1 and 3. So is that how we define a function? If we put something in, we get 2 things out? No. So we have to have a unique output for every input. So this is not a function. It's a relation. It's fine to have a set of ordered pairs, but it's not a function. So are you telling me that I can't find an inverse for a parabola? That's interesting. Well, we'll look at that in a minute. But right now it says it doesn't have an inverse that's a function. So we may look at this in a little bit. So do I have to really go through this whole process here every time I look at a graph? And the answer is no, dude. There is a visual way to do it. There's a way to look at a graph and tell whether the inverse is a function or not. Okay? So the answer here is, can we look at a graph of a function and tell that it has an inverse? Yes. All right. So how can we do that? Well, let's draw a horizontal line through y equals 4. And I think you'll see why I chose 4 in a minute. Well, because that's to kind of fit with the points we were just looking at individually. So here's 4. I use my little studio bookmark to help me draw the horizontal line through 4. So if you can just sort of remove the x squared graph from your mind and just look at the straight line. If I say, how many times does, I'm really bad at drawing straight lines. Look at that. It's definitely got a tilt to it, right? How many times does this red horizontal line intersect the graph of f, which is your straight line? How many? Just once, right? Just once. In fact, where does it intersect that? Let's see. When is the output 4 on my straight line? Well, when x is 3. When x is 3, my output is 4. There it is, right there. It's that point. Okay, 3, 4. So how many times does it intersect? Just once. And what did we say about the function f? It has an inverse that's a function. I wonder if that has any relationship to this idea here. Well, we'll see. How many times does the red line intersect the graph of G? That's the parabola. Twice. And this is our oh no case. Oh no. Okay. Because we said that if we have the situation where we have two different inputs, we had -1, and when we subtract 1 from it, we get -2, and when we square that, we get 4. So we had this point right here on our original graph, -1, 4. We also had the point 3, 4 on f. This is on our function f. These 2 points are on our original function. And what happened was when I tried to swap them to see what the inverse would look like, when I tried swapping their points around, I noticed that I did not get a function, I got a relation. So what happens here is if you have 2 different inputs in your original function, -1 and 3, and it brings you to the same output, that will define a function, but it's going to tell you that it's not going to have an inverse that's a function. So anytime you draw a horizontal line through a graph and it hits your graph more than once, then the function does not have an inverse function. We'll always have an inverse, it's just a relation, but you can't describe it in functional notation. So we refer to this visual test as the horizontal line test, or shortened HLT, not BLT, it's HLT, okay? So the horizontal line test determines whether or not you have a function that has an inverse function. Ian?
Okay, so you can take the inverse of the quadratic, but
You're going to have to do something to the, so in other words, if you have different inputs into your original function, you must have different outputs for there to be an inverse function. So if you think of this straight line, every single input you have has only one unique output, right? But in your parabola, you can pick 2 different inputs that have the same output. So when you reverse that, it's not going to be a function. Okay. Yeah, Sonia? I picked 4 just because I wanted to come back here to the points that I originally picked. And in my original 4 points here, I had 2 inputs that gave me the same output. I could have done the same thing with -2 and 9, but I would have had to go up here to 4. If I put 4 in here, 4 take away 1 is 3, 3 square is 9. So there's going to be a whole series of pairs of points, Sonia, on a parabola, except for your first point, 1. It's just going to be 1, 0. There's always going to be, because this is symmetric about the line y equals 1, there's going to be an infinite number of pairs that have the same output. If you think back to your x squared, you got 1 and -1 brings you to 1. -2 and 2 brings you to 4. -3 and 3 brings you to 9. So there's going to be a bunch of pairs of points that bring you to the same place. So if you're looking at a graph, this horizontal line test, boom, it's quick, okay? If you're thinking about it, you just say, if I put in a different value for x into my original function, will I always get out a unique output? Anytime you have a straight line that's always increasing, you're going to have an inverse function. If you have a straight line that's always decreasing with a negative slope, you will have an inverse function. Any function that's always increasing throughout your domain or always decreasing will have an inverse function. But look at this. This is decreasing, and then it starts to increase. So there's going to be symmetry here. So you're going to have, for 2 different x values, you'll have the same output. That says it doesn't have an inverse that's a function. So I could show you what we do in this situation, and I will at the end of the lecture. I'll show you how we handle parabolas. Okay. So the horizontal line test, oops, don't I have, yeah, here. So the horizontal line test is for an inverse function. How do we test whether something is a function? Vertical line test, right. So a horizontal line test says that a function f will have an inverse that's a function if there is no, that should say no, not. If there is not, no, it's okay. If there is not a horizontal line that intersects the graph of the function in more than one spot. So it's a very quick and easy test. You just draw a horizontal line right through your graph, and if it hits it twice, no go. So here's two examples here. Here's our first function. And in a little while, you're going to learn what the formula for a function like this may be. This is a polynomial function. So what do you think? Does that first function have an inverse function? Why not? Does not pass the horizontal line test, right? So any place, in fact, I can draw zillions of horizontal lines through here that shows that it fails. So if I draw this one, you can see it hits it at 1, 2, 3 spots. So with this function, I can put in different values of x and still come right up to 4. So this fails the horizontal line test, the HLT, so it does not have an inverse function. Okay, you're going to like these on a quiz or a test, right? Just draw a horizontal line through. Brendan?
So let's say you were to give us a point.
Okay, hang on. We're going to get there. Okay, I don't want to confuse people just yet. But that's going to be the workaround, you know, the go around, right? You don't like the bureaucracy, we'll work around it. There's a workaround. Okay, so unfortunately, this picture didn't come out all the way on. I don't know why this is happening now, but it's just started happening. You have this picture beautifully drawn on your lecture notes. It looks something like this. Okay, so that's a cubic. And does this have an inverse function? Sure does, because any horizontal line that I draw through the graph of this function hits it in one spot, so we're golden. So this is yes, it has an inverse function. Because different outputs have different inputs. So you're looking at the outputs now. Different outputs have different inputs. That's another way to say it. Whereas if you look at this first graph, different outputs don't have different inputs. Okay. I think I said that backwards. Different inputs always have different outputs. That's what I should have said. So here it is. It's easy to look at. It's a little harder to like write mathematically, but this is what we were talking about a minute ago. A function passes the horizontal line test if the following is true. If you have two values of x in your domain that are different, then the values of the function, your outputs will also be different. You'll never get the same outputs for two different inputs. Whereas when you have a parabola, you can have different x values and wind up with the same y values. So that's why a parabola or this type of polynomial does not pass the horizontal line test. So if you have different inputs, you have different outputs. Any type of function that satisfies this criteria is called a one-to-one function. Every one-to-one function has an inverse function. That is going to be a truism for the rest of the class. So every graph that's one-to-one has an inverse. And what that means is if you had a picture of its graph, it would only be intersected once if you drew a horizontal line through it. So not only does this horizontal line tell you you have an inverse function when it intersects once, it also tells you that your original function is what we call one-to-one. You put in an x and only one x. If you put in two different x values, two different y values come out. And you can, I think you can see that if we take our parent function x squared, and I put in, we can all agree that 2 does not equal negative 2. Those are two different inputs. But if I look at f of 2, it equals f of negative 2. So that tells you that this is not 1-to-1 because 4 equals 4. So this is not 1-to-1. So the idea here is two different inputs, you absolutely get two different outputs. And all of your parabolas fail this. And you can just think of the graph if you want to, if you don't like the mathematical way of looking at it. Okay. So we now know when a function has an inverse. So let's say I give you a function and I say find its inverse. Well, the first thing you'll probably want to do is pull out your calculator or throw it into GeoGebra and look at its picture to make sure it has an inverse before you start doing all your work. So let's figure out mathematically, if we have the equation of a function, how we're going to actually come up with its inverse. Now, previously to this point, we've had a finite set of ordered pairs, and we've just swapped the inputs and outputs, and that's how we've created the inverse. Now we want to do it for an infinite set of ordered pairs. That's called a mathematical function. Okay, so your textbook refers to this. I think it's kind of a little clever idea here that your textbook, I've never heard this until I read this textbook. I mean, we've done it 1,000 times, but they call the process that you use to find an inverse the switch and solve strategy. So what are we switching, and then what are we solving? So here's an inverse right here. Excuse me, here's a function. It's a linear function, 5x minus 6. You could probably picture this in your mind. You go through 0, -6, that's your y-intercept, and then you increase at the rate of 5-to-1, right? That's your slope. So it's going to be a pretty steep slope. Well, not that steep, 5, but it's not 1 or 2 or 3, and it's not 100. So 5x minus 6. And in fact, right now, we can figure out this strategy without any, the inverse without any fancy work because we just did it. If I ask you, right here, I'm going to cover up f of x, what has happened to x? What would you tell me has happened to x? And to answer that, think about what would happen if I gave you a value for x right now, like 2 or 3 or -1, and you were to evaluate this. So what has happened to x? Can someone tell me what's happened to x? Go ahead, Sonia. Yeah, and what else? To get the full answer, what else would you do? Right, because if I gave you a number for x, you would first multiply it by 5 and you would subtract 6. I want to undo that. So now what would I do to undo it? Add 6 and divide by 5. Okay, so we have a sense already of what our inverse function is going to look like. Here's our original function. Is 5x minus 6, f of x equals 5x minus 6, going to pass the horizontal line test? Yeah, because it's a straight line, always increasing. So every time I put I have two different x's and I plug it in, I'll get two different outputs. So this is going to have an inverse that's a function. Let's see how we find it. So here's where our switch takes place. So we're going to start off with our original function, f of x equals 5x minus 6. The first thing we're going to do is we're going to replace f of x with the letter y. That's the first thing we do. Then we're going to, since x and y swap their positions when we change the inputs and outputs, we're now going to do the switch. We're going to, everywhere we see a y, we're going to write an x, and everywhere we see an x, we're going to write a y. So we interchange the x and y, and now we solve for y. So we just solve this equation for y. And that's what you've been used to doing all the way along. You can solve this for y by, you would add 6 to both sides. And then your result, x plus 6, should be put in parentheses, because if x was a number, you'd just call that one thing like 10 if x is 4, or 0 if x is negative 6. So put it in parentheses because it's a result. And now the last step you would do is to divide everything by 5. So y equals x plus 6, the whole thing divided by 5. And that's what we just said we would do. We would add 5 and then divide it all, by, add 6 and then divide it all by 5. So we didn't even need these fancy steps. We could just think about the doing and undoing. So the last thing we want to do now, we can't read it here because I don't know why this is happening. I'll have to check with IT, but it must be a new version of Smart Notebook that's cutting off these pictures. So what's the last thing we want to do here? We solve for y, we did that, and what's number 4 say? Well, the next thing we want to do is just put this in functional notation. So you want to say y is f inverse of x. That's x plus 6 over 5. So here's what we're claiming is the inverse function. And that's just a straight line as well. So you know it's a function. It's a linear function. And now you have to verify by doing the composition of the two functions. So f of f inverse of x, put the inverse in for f. So 5 times f inverse of x, take away 6. And then that has to come out to be x. So let's see if it does. So 5 times f inverse is x plus 6 over 5, take away 6. The 5's cancel, and I get x plus 6 take away 6. That gives me x. I'm a happy camper. So the first composition works. Now let's try the second one. Now my inverse function is going to be outside, and my function f is going to be my inside function. So I put f of x every place I see an x in my inverse function. So my inverse function says x plus 6, so now it's going to be f of x plus 6 all over 5. And what's f of x? F of x is 5x take away 6. And when I remove those parentheses in the numerator, I get negative 6 plus 6 gives me 5x all over 5. And there's my x back. And now I'm a really happy camper. So I've just proven that these two functions are inverses of each other by doing the composition of a function with its inverse and then reversing the order of the composition. So what I'd like you to do now at your seats is find the inverse of number 8. Try to work through these steps one at a time and find the inverse of x squared. Is it x squared? I don't have my glasses. X cubed plus 1. Thank you. Let's quickly go through the steps. The steps say to take your original function, replace f of x with y, then do your switcheroo. You switch your x and y, so you get x equals y cubed plus 1. Switch and solve. Now solve this for y. So it's x take away 1 equals y cubed. Anytime you get more than one term on the left-hand side, that means you got adding and subtracting. Put that thing in parentheses. And now you undo y cubed by taking the cubed root of both sides. And now you replace y with f inverse of x, because that's what you have just found, the inverse. Okay. So good. All right. So what if we're looking at the graph of f and we want to draw its inverse function? So we look at a graph, and now instead of finding the equation for its inverse, we want to know a quick and handy way of drawing its inverse function. So let's take a look at that. So here's a function of, we don't know what the equation is of this function. If you've had some math before, you might have a sense of what type of equation that is, but it's not necessary to finish this question here. So we want to see how could we actually draw the inverse? And that's why I've given you these little toolboxes. So if you could take out of the toolbox a ruler and a colored pencil, or if you have your own set of colored pencils or pens, that's great. Okay, so here's our function f, and since we know the inverse function has the, if we take points on our original function and we just swap the x's and y's, we're going to create the inverse of that function. So if we take our original function and we have some nice points that we can easily identify and we swap the x and y values, we are going to get the inverse, a picture of the inverse function. So list a few nice points on the graph of f that you can look at and identify the coordinates for. Anybody give me a couple of points real quick? Yep, Kyle? 1, 1. What'd you say? 1, 1. I don't think it's 1, 1. 0, 1, right. That's all right. I do this all the time. 2, 4. Okay, that's a nice point. 2, 4. Let's see. 2, 4. Yep, definitely nice. 3, 8. 3, 8. I feel like I'm in a bingo parlor. Okay, 3, 8. There we go. Any other nice points? 1, 2. Yep, that's pretty nice. 1, 2. Okay. And as my x values get to be negative, 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 what's happening to my y values? They're getting really close to the x-axis, right? Okay, so all I do is I reverse these coordinates to get my inverse function. So now I'm going to use a different color, and if you have a different pencil from your kit or a pen, let's just reverse these. This is what we were used to doing on Wednesdays, just reversing each of the inputs and outputs in my ordered pairs. And now I'm going to graph those points. 1, 0 is right here. 4, 2 is right here. 8, 3. 8, 3 is right here. And then 2, 1 is right here. And as all my x, if I had a bunch of negative x values, those would now be negative y values. So I start to connect these like this. And then I think about taking my different negative values, and it's going to get really close to my y-axis now instead of my x-axis. So that would be, this is f inverse, and this is f. So what did you say, Eric? It looks like I flipped it across the diagonal line. What would that be called, flipping it and having the point over here meet a sister point over there, or a brother? Huh? It's flipped? What's the word we give? Reflect, right. We've reflected it across the diagonal line. What's the equation for that diagonal line? Y equals x, right. So if you want to find a function, I'll get to you, Sonia. If you want to find a function, it's basically a reflection across the line y equals x. Notice, if you drew a line between these, the point and the point of its inverse, the distance would be the same from your point to the line y equals x, and then that same point on y equals x to your point on your function. Those distances are the same, or congruent is the word we use in geometry. Sonia?
Is this the same, like if you had that on a paper and you folded it?
Yes. Over that line.
Yeah, over the line, it's going to just give you
a mirror image. Yep. You know what is amazing to me? Some students can look at the original graph. I used to bring in little mirrors. They're like these little red mirrors, and students would put them on the line and then look through it and draw it. Some people have the ability to look at these functions, and the visual image of this function inverse is there for them. It's amazing to me. That I don't have that ability. I've gotten better because I've been doing this for a long time. But I have students that the algebra is kind of like, but when they see the image and they can just do it like that, it's amazing to me. So we plotted our points, and note that the graph of the function is symmetric or reflects about this line y equals x. That's your identity function. That's what you worked with on your project, f of x equals x. So what if you have something funky like this? Well, that's why I've given you your kits. Draw your line y equals x in. We know what the points is of y equals x. Okay, just draw in a few points for y equals x. Okay. 1, 2, 2, 4. Okay. Draw your, you can make it a dotted line if you want. Okay, so this is a piecewise function. Then you identify a couple of nice points on your original function, and I've done a few of those for you right now. We have -1, 0. We have -3, -2, and we have 4, 2. You might want to put a few more in if you can find them. I think -2 looks like it's -1. Okay, and now swap. Do your swap-aroos. Okay, so we're going to swap-aroo, and I'm going to call this my inverse function, which I'll highlight with a different color, red. And it will be 0, 1, -2, -3, 2, 4, -1, -2. So now I plot that. 0, -1 is here. -2, -3 is here. 2, 4 is right here. And -1, -2 is right here. Okay. And anything else that will help me draw this line, you think? So look, if I'm going equally distant, right, symmetrically across that line, then we go up to like that point there. And there we go. That's our inverse function. So they're not too bad to draw. Okay, you just got to take your time, identify some points, and make sure that your distance from a point to its point across, reflected across that line, y equals x, is equidistant. So once you get the hang of it, you can just zip it through. Now, I didn't plot all the points. I just got the idea and connected my points. Okay, I think what I'm going to do is I'm going to leave this idea that we started off with the parabola, and does it have some way, can we do something to this parabola so it has an inverse? I want to save that for Monday because I want you all to have a chance to work on your activity before you leave today. So we'll do this on Monday. Okay? So you have a bunch of inverse functions here that you're asked to find the inverse for. Please read the instructions here. Don't try to find the equation for the inverses for 5, 6, 7, or 8. They're very time intensive. So you've got a series of these. You want to determine whether, first of all, the function's one. What if you draw a horizontal line test through one of these and it's not one-to-one? Do you continue on to try to find its inverse? No. I'm just interested in the inverse function right now. Okay?